Hello and welcome to my perfectly normal, nothing unusual video about spatial derivatives. In this video, nothing unnecessarily exciting will happen. It is just one nerd and their whiteboard talking about derivatives. So we've got your position in space, x. That's what I'm going to call our position, and I'm going to measure it in meters. But what if we want to take the derivative? Well, the derivative is just the rate of change over time. So that would be dx dt. Which means if we've got a small amount of change in position over a small amount in time, what is that? Often call it your velocity. I'm going to call it speed because we don't care about direction, and that's in the meters per second unit category. What if we want to take the next derivative? Well, this is acceleration, which you might know from the accelerator pedal in a car. If you're American, the gas pedal, which stands for Greater Automobile Speed Pedal. So checks out. Now that's if we differentiate with time again. Now the little secret, what it's actually doing is you're putting another d dt, which is another differentiate with respect to time, at the front of your previous dx dt. But because mathematicians are mildly lazy, you don't worry about all this. You pop a squared on the d, you pop a squared on the dt, and you're in business. You've now got acceleration, which I'm going to abbreviate to acceleration, and that is in meters per second per second. Meters per second squared. So far, so standard. But what if we take another derivative? Well, of course we can do that mathematically. There's no reason why we should stop there. Over here, we know the pattern just continues. It's going to be d cubed, that's the worst three I've ever done, dt cubed. It's going to be in meters per second cubed, and it's going to be the rate of change of acceleration. And if you're familiar with that, you know that is called the jerk. Yep, you got it. And this is not a perfect analogy because of friction, but a jerk is when you move the acceleration pedal around. But how fast are you moving it around? What is the rate of change of jerk? Well, of course, we can have more and more derivatives. The next one down, oh goodness, I think I can just fit in the fourth power, d to the 4 over dt to the 4, which is going to be in meters per second per second per second per second. What's that called? What do you call the rate of change of jerk? Well, if you change being a jerk, that's an O snap situation. Rate of change of jerk is snap. Rate of change of snap is crackle. And after that is pop, because physicists just think they're that funny. But as a mathematician, I'm obviously familiar with the theoretical derivatives, but I want to actually experience them. I just haven't got a need for speed. I've got a need for speed and its higher order derivatives. Can I do something and log some data so I know if I've definitely experienced jerk and indeed snap? But for that kind of crisp rate of change of the rate of change of the rate of change of the rate of change, I can't just get in a regular road legal car. No, I have to go into the world of motorsport. And something like Formula One might do the trick, but if you want true, pure acceleration and its higher derivatives, you want to go on a motorbike. You want a MotoGP bike. That's when I'm going to experience jerk and hopefully snap. So I guess to continue this video, I need to go ride a Grand Prix bike. So I'm going to ride a Grand Prix bike. I'm here at the British round of MotoGP at Silverstone Racecourse as part of the Cosmic Shambles documentary about speed. I'll link to that below. And they're actually going to put me on a Grand Prix bike. It's one of the Ducati bikes from the 2012 season, and they're going to send me around. Oh, there we are. That's easier to talk. Send me around the Silverstone racetrack so I can enjoy some extreme data collection. Yep, I'm a bike guy now. No, not at all. As I mentioned, that was because I was helping out with the documentary. You can watch the whole thing. I'll link to it below. And if you want to have a go at that, it's It's run by a charity called Two Wheels for Life. They will occasionally auction off the opportunity to do exactly what I did, which is mostly motorbike people who do that. In the training, they were saying things like, now of course, reposition your weight and look into the apex just like you would when you're riding your own bike. And I'm like, I ride a very different type of bike. But they let me keep the gloves. These will be great for when I'm cycling, is what I thought but did not say out loud. Never one to waste a data logging opportunity separate to the documentary on my phone. I just happened to be running an app which dumped all the data from all the sensors, including the GPS and the accelerometers, into a CSV file. So afterwards, we can have a closer look at it and see not only how fast did I go, but what level of derivative did I definitely experience. I'm going to take these off now. First thing I did was just pull off the GPS, which is updated once a second and gives you the latitude and longitude. And I just did those as a scatter plot, and very pleasingly, you can see the path I went around. It looks like there's a gap here, but in the data, I mean, that's just kind of what, I mean, also you've got like all these clumpy bits. So in theory, this is the Silverstone racetrack that I've gone around, and up here at the top is where we started and stopped. And then, I mean, this should follow the shape of, well, let's check it. You know what? Let's check it into Photoshop. 1 second. Okay, we're in Photoshop. I've just got the plot from before. And over here, I went to Wikipedia from the 2022 British MotoGP thing. And I got an outline of the track. So we're going to copy the track. That's the original one off Wikipedia there. And I've just orientated it with north up, so it matches my latitude and longitude here. And let's have a little look. If we pop that in the corner, look at, okay, if I don't change the aspect ratio, that's, maybe my plot, maybe the ratio, that's not bad, look at that. That's kind of close. It's not the worst. I mean, you can definitely see the dots are roughly the outline of the track, give or take. And GPS, I mean, it's once a second. It's not outrageously accurate. It's accurate enough, but it's not super accurate, which is why we're not getting an exact match to the shape, why there's some weird clumping here and there. Like all these dots there, that's just me going around quite a tight corner. You know, the one, that corner on Silverstone, they've all got names. And the gap here, I know something went wrong, so who knows. So GPS is pretty good, but not amazing. It does also record the speed. So I should be able to get the velocity with the speed from the GPS, and that's log separate, and that traditionally is more accurate because it's not an absolute recording, it's a relative measurement. So we'll bring that up. Here it is. Let me talk you through what I've done in this spreadsheet. I've got the exact time and date that each bit of data was recorded. Annoyingly, that's all text. So reference time is me just pulling that out and turning it into seconds. And then here, my absolute time is how far through the journey around the course. And I picked a time to start roughly near where I began moving. And then this is each interval. So the actual data that's being recorded by the app is 100 times a second. But the distance and the GPS and the velocity from that only updates once a second. So we'll get to the higher resolution stuff later. And then what I've done over here, I'll scroll down a bit. You can see now I'm actually moving and doesn't update that often. And then over here, I've worked out the amount I will have moved from that tiny bit of time at that speed. And when I add them all together, you can see my lap was 5.560 kilometers. And Silverstone is 5.9 kilometers. So we're within 10%. Like that's pretty, I think that's pretty amazing. GPS, and this is not super accurate, but if you actually work out the area under this plot, this is my velocity plot, and it's all quite chunky because it's only once a second data. If you add up all the area under there, it's within 10% of the actual distance around the track. And I think that's actually quite amazing that you can just put a phone in your pocket and get a measurement that is that close. But this is not good enough. Like the resolution is not fine enough to be able to look at acceleration. with enough resolution to then get jerk and snap. So we're gonna have to do something else. But before we move on, I'm just gonna, you know what? I wonder what my max speed was. Let's find out. The maximum of all the speeds, and this will be in meters per second, was 72.25. And I think that's gonna be pretty accurate. So let's just look that up now. Okay, 72.25 meters per second in kilometers per hour. So my max speed was 260 kilometers an hour. Oh my goodness, what is that in miles per hour? I was doing 161.6. I was doing 100 times the golden ratio miles per hour. That's so stupid. And the reason it's so incredibly fast, by the way, is that was an actual like retired racing bike. So, you know, in my, everyone's got a copy of the Motocross book from 2012. This is the year that that bike was actually racing. And so in here, I can find a photograph of the exact bike. There it is. That's the bike I was actually on going around the course. So they converted it to be a two-seater, and by converted it, made a mildly bigger seat and welded two tiny handles to the fuel tank. Thanks a lot. So I was on that actual racing bike, which is why I was going at such insane speeds. And I've been asked to point out that that's a race-worn helmet from the 2012 season, and that is not it's not 2008 season. I've just been told 2008 season, and this is also a 2008 bike. 2007 bike. As you can see, not yet a fully fledged bike person. And now we pick up the pace by moving on to acceleration, which is a whole other thing. Because the accelerometers in the phone, very cool, they're logging 100 times a second, roughly, but as well as getting the acceleration in 3 different directions, I'm also getting the angle the phone is on with its pitch, yaw, and roll. That's the other one. And we need to be able to convert from the 3 different acceleration components in the phone by using the angle of the phone to work out in the reference frame of the bike. And of course, you've got gravity making the whole thing a complete mess. The phone does a little bit of the lifting for you, but a bunch of the heavy lifting, mathematically speaking, has to be done after the fact, which I was not able to do, so I asked very nicely. I have a podcast called A Problem Squared that I do with Beck Hill. Normally we solve other people's problems, but we also ask our listeners to help with our problems. And I put a call out for people who could take my CSV and do something nice with it. So I want to very quickly thank Cass Weiser, Dom Wilson, and Jan Wolf for giving me a hand and crunching the data and sending through some nicer versions, which I've then had a bit more of a play with. So all the final inaccuracies are absolutely mine, but here it is. This is the acceleration data in the direction the bike is pointing. So this is not the acceleration that's leaning me into the corners. It's not any of the up and down movement. This is pure forwards and backwards down the central axis of the bike. And I've plotted it so you can see at the beginning the acceleration goes up. That's me accelerating straight down the line. And then there's a lot of positive, there's a lot of negative. Oh my goodness, there's a lot of negative. You can see down here, that is more than 1g deceleration, and actually there's slightly more than a g acceleration over here. I think I got to like 1 point. Oh, we can find out. Let's find out. What's the max of, that's the acceleration in g there, and that's the min. So actually I'm at, I think I hit like 1.1 g was the most I had, which is, I mean, the maximum that the actual riders have in a proper race is apparently about 1.8 g in terms of acceleration, deceleration down the line of the bike. And so, I mean, I'm not at the max, but that's still, it's a lot. It's a decent percentage of the total acceleration. Now, before we move on to see if we can take the derivatives of the acceleration to get the jerk and the snap, in theory, we should be able to integrate this. We should be able to take the area under this and work backwards to get velocity. We should match the velocity we got from a completely different sensor from the GPS. So I thought, you know what, just as a little bit of a validation of what's going on, I'm going to integrate this first and get the same velocity plot, but through in a completely different means. And here's what that looks like. It's not great. So, I'll talk you through this plot. So this is the velocity plot here in meters per second, and it kind of matches what I remember happening in the race. That's us taking off from the line. That dip there was the rider doing a wheelie down the first straight, which is why the velocity flattens out for a second, and then the acceleration kicks back in again, and then so on and so on and so on. Now you may notice at the end of the ride, we are way, way, way up here, and that's because we've got all these values. We're taking 100 a second. There's a lot of inaccuracies that are going to add up. So this is why you've got the GPS and you've got the accelerometers. The accelerometers are good in a moment-by-moment basis, but the cumulative errors are pretty horrific, whereas GPS is not particularly good moment-by-moment, give or take, depending on what you're doing, but it stays the same over time. And so I was like, oh, well, how am I going to compare this? So I'm still confident this is great on a moment by moment. We'll still get our jerk and snap that I experienced because those will be very fleeting. But I really wanted to see if I could match this up properly. So down here, all I've done in this plot is take the top plot and over time try to compensate for the drift. Which is not perfect. It was a really lazy linear correction. I assume that the accumulating error is linear over time, and I've just deducted it and it's given me this. And the question now is, how close is that to the GPS one from earlier? And it's not wildly different. I mean, GPS, there's going to be some lag in there. It's very low resolution, but you can still see accelerating off the line, wheelie, and then it rapidly catches up. Whereas here we've got a much smoother curve. So I think on a small scale, the shape is better on this one, but the long-term accuracy is better on the GPS one. So what's really nice is I was able to show we get exactly the same shape plot two different ways by either taking the GPS location and its derivative, the velocity, versus the acceleration and its integral, the velocity. It's a fundamental theorem of calculus moment. To recap, I'm quite confident in the acceleration data on a moment-by-moment basis, so we are going to do some derivatives. I will say, however, that having a phone on a vibrating motorbike, which is basically an engine with a few trivial wheels, it's not the best way to collect that sort of data, and so we did have a lot of other vibrations and things to be removed, and so the acceleration data, as well as being converted to the bike's reference frame, has been filtered a lot to try and take out the frequencies coming from the motorbike. In fact, a huge debt to Dom Wilson. I'll be using Dom Wilson's filtered data for the rest of my analysis. So again, thanks to everyone who helped out with the data, even the people who had a look at it but weren't able to do anything. I appreciate everyone who gives it a go. But now we are going to take this plot here, which is our acceleration plot, and then we're going to take its derivative to work out the jerk in the direction of travel, which looks like that one down there. So I've put an extra column on where I've just worked out how much it changes between data points and the time interval between them. And there, I mean, does that count? I think that's a very abrupt negative jerk. Oh my goodness. Yeah, that's a jerk where I'm really slowing down. And there's some pretty clear jerks early on over here. So I wonder what that was. That's me going real slow. You know what? Let's see if we can match that back to the GPS coordinates and work out what was happening. So that jerk came at 93.4 seconds into this data set. So if I go back to GPS and I come down to 93.4 seconds is here. And so that's when I'm at 52.7 and negative 1.01. I don't know if is that low enough resolution to be able to see it. 52. That's it there. It's this part of the track. Huh. I mean, it looks like it's a pretty sharp corner, but you know what? We'll look up the footage. We'll see what was happening then, and we'll play in the moment when I was a maximum jerk. All right, so I'm now convinced that there I experienced very distinct jerk. I think actually these points here are non-trivial. A lot of these smaller ones, that could be noise in the data. Let's go one further though, see what our snap looks like. So there's our jerk, and this is the snap column I've put in there, but I haven't plotted it yet. I thought we could all see it together. So what I'm going to do is duplicate the jerk plot, pop that down here, and then I'm going to move it one over. So instead of being the data in column L, I'm going to move it to column M. So we go in here and we change the data. So that's now column M. And we're plotting M against the same horizontal axis, and it looks a little bit like this. Oh! Wow, that is real quiet and then real big. So look at this. That is a lot of snap. Okay, I mean, I know snap is all, oh snap, but that's too much snap. I think that's noise in the data. I mean, I believe in the jerk because when we look at the footage, but these snaps, yeah. I think now we've just hit mess in the data. I could be wrong. Not a professional at this. I don't think I could say just by eyeballing this plot, having been messed with by me and filtered by other people, I don't think I can definitively say that's a snap, but I will say that's a jerk. Okay, just had an update from behind the camera. Trent, my MotoGP consultant and writer-director of the documentary I was in, saying that corner is the most kind of acceleration, deceleration you're going to get on the course, apart from, I guess, maybe starting. So maybe snap. Let me know in the comments below. We'll do a vote. If you think I am allowed snap, just at some point in your comment put, oh snap. If you think I'm not, I'm being a jerk, put, you're being a jerk. And that'll be that's how you decide things in physics. You take a vote. Pretty sure that's how science works. That's it for my nice boring video about spatial derivatives. Thank you so much for watching this. Hello to all the students watching this in a lesson at school. Thank you so much to my Patreon supporters who make this possible. Please do check out the documentary, Rapid Motion Through Space, made by the Cosmic Shambles folks. Although Trent's sitting right behind the camera right now. Go watch it. It's on their website. And huge thanks to Two Wheels for Life, the charity who got me on the bike. That was great, and loads of other people. I mean, using footage from Silverstone on the actual race weekend is a non-trivial task in terms of both my bravery and admin. So we're going to thank everyone below in the description. Please do check that out. And that's it. Thank you for watching. I hope you enjoyed this lesson about derivatives.